Okay, so maybe some people got scared away by Florence. Maybe people just aren't going to stop coming. I guess we'll see. Are there any questions about anything, homework, otherwise, before we start? Nothing? Okay. I just did want to say one thing. I should have said this in the first class, but if you send me an email and you don't get a response, give me 24 hours to respond. If you don't get a response, send it again. So I never purposely don't answer your emails, but once the semester gets rolling, I get a lot of emails from a lot of students, and sometimes there's chain emails and I lose track. So don't ever hesitate. Don't ever think I'm not responding because I don't want to. Give me 24 hours and send it again. Other than that, well, I did have somebody asked for the square root problem in this coming homework. How do you take the derivative? You have the function x squared minus a. So you have the function x squared minus a. And how do you take the derivative? You need to take a derivative to do Newton's method. So you could just do it by hand, right? So 2x, you don't have to use, and in this class we won't use symbolic differentiation at all, although it's a very nice thing, but in this case, feel free to hard code 2 times x. I think that's about all. Can't think of anything else. Okay. So today, kind of the agenda is we're going to start by talking about kind of the general iterative optimization algorithm. Oh, let me turn up the lights. All right, so we're going to talk about the general iterative optimization algorithm. And that'll lead us to talking about steepest ascent or steepest descent, the steepest ascent / descent algorithm. And then we'll talk about multidimensional root finding. And then we might have time for one more thing, but I'll leave it at that for now because I'm not sure that we will have time for one more thing, but maybe we will. Well, so if we do have time for one more thing, we'll talk about Newton's method, or we'll talk AX = B. We'll decide what we're in the mood for at the end of presenting class. Okay. So I wanna focus for now on numbers 1, 2, and 3, and put it in a greater context for you where we are. So in general, we're thinking about optimization, and we will always be thinking about some function f of x from some n-dimensional space to R, right? So our functions are multidimensional in their domain, but never in the range. In the range, they're finite dimensional. Maybe at the very end of the semester we'll change that, but this is the type of functions we're thinking about. And then we want to minimize. We've been thinking about minimize f of x for x in Rn. But sometimes we want to maximize, and so let me just ask you, do we need to have 2 different theories of like minimization theory and maximization theory? Like, so why are the 2 equivalent? If you know how to minimize a function and I ask you to maximize, what would you do? Do the opposite. What does that mean? I think I heard somebody say it. You take the negative, right? So if you want to, let's say I want you to minimize f of x, but you spent a whole semester learning how to maximize functions, and that's all you know how to do. Well, you're good, because if you want to minimize f of x, that's the same as maximizing negative f of x, right, for x in Rn. So through the semester, we'll switch back and forth between minimization and maximization, just based on the application. So for example, just to put that in context, for linear regression, we wanted to minimize the loss function, L of alpha. So we wanted to minimize it because the loss function was the sum of squares. And we aren't quite there yet, but for logistic regression, we don't, properly speaking, we're not using a loss function, we're using a likelihood. And a likelihood, although it also has the letter L, you want to maximize the likelihood. So for the logistic, we'll maximize, and I'll also write L of alpha, but the L's are different, right? So for the top one, it's a loss function that represents least squares, and for the logistic regression, it's a likelihood. So depending on the application where we are, we'll switch. But most optimization textbooks only minimize, and because, just to be consistent. Okay, so where are we in terms of our optimization? So we've noted the following. First, if f of x is quadratic, then we can solve grad f of x equals 0. Right? And in fact, so solving that grad f of x equals 0 reduces to a matrix by matrix inversion. Right? And so I won't go through it again, but you guys have done it for your homework. If I give you a quadratic, in standard form, you take the gradient, you set it equals 0, and you solve, and you get that kind of, the negative 1/2 A inverse B, right? So that's the matrix inversion. Okay. So that's great. And that's for linear regression with the least squares, I should say. It's really a sum of squared errors, it's loss function. But then what I hope if you've started the homework, for logistic regression, L of x, so I guess I should write this as L rather than F. But for regression, L of x is not quadratic. So for logistic regression, L of alpha, so let me write L of alpha, is not quadratic. And you can note kind of two sub things here. One is you can write down grad L of alpha, and in fact you're doing that for your homework. It can be computed, written down, / written down. But what I hope you're convincing yourself of in this homework, if you haven't already, is that you can't solve it analytically. You can't do like substitution, but we can't solve, that's a can't solve, grad L of alpha equals 0. This should be alpha. So I'm mixing my f of x's and my L of alphas. Okay, so that's the state of affairs right now. Any questions? All right, so this second thing is much more common. Most functions are not quadratic. Most functions you can write down their gradient, or most functions we deal with, I should say, we can write down their gradient, so we can do that sub part 1, but we can't solve it. So then, essentially, there's two things you can do. That's a bit of a simplification, but essentially there's two things you can do, and then there's all types of twists, kind of combinations of the two. So what do we do? There's two things we can do. So what to do? One thing you can do is say, okay, I really want to solve that grad L of alpha equal to 0. I know, I was taught in Calc 3 that this is how I find, this is actually how I find critical points. The critical points are where maximums happen. So I'm going to solve this, right? This is what I'm going to take as my core. So if you focus on that, if you say, okay, what I'm going to solve is grad L alpha equal to 0, then what you're doing is you're going to do root finding. It's not the same root finding we talked about last week, because last week we talked about one-dimensional root finding. You have a very simple function. The gradient of the loss function, or the likelihood, is a vector. So it's actually multidimensional root finding, and we'll talk about that. But that's one direction you could go. And this direction leads to what's known as Newton's method. Newton's method is confusing because there's like 50 things that's named after Newton. So there's a lot of things named after Newton. So but we'll sort that out. All right? It is, but it'll look different. And we'll talk about how they are actually the same. Yeah. Okay. All right. The other thing you can do is what I think most of you would do. So if I took you and put you in a forest, so you can't see the topography around you, and I told you I want you to get to the top, there's a peak around you. I want you to get there. What would you do? Right? So like your altitude, think of that as your function, and your longitude and latitude are your coordinates. So you're in a two-dimensional domain, and you can walk kind of north, south, east, west, and that moves you up or down in altitude. But you can't like look. You can't go up in a helicopter and look around and see everything. You're in this big forested area, and I tell you, find me the mountaintop. What would you do? You'd walk uphill, right? You'd say, okay, the forest goes up that way, I'm going to walk up that way. So that's the other philosophy. Suppose if I want to maximize L of alpha, what I focus on is this maximization. So I focus on L instead of finding a root of gradient. And that leads us, it leads to many different algorithms, but the one we're going to talk about today is steepest descent. Okay? And a lot of the course will be the tension between these two. Each one has its pluses and minuses and works in different settings. Okay? All right. But any questions on that? Yeah.
So what's steepest
ascent?
Ascent.
Ascent, yeah.
I don't know what it's
Ascent means going up.
Oh.
Yeah. Any other? Okay. So, but what I do want to do then, there is kind of a general framework under which you can place both of these. So I want to first talk about a general iterative optimization. Because both of these, whether you do Newton's method or whether you do steepest ascent, are going to be iterative optimizations, right? So we have this huge class of iterative optimizations. Those are two examples. So let me introduce you to that, just that general idea. So here's the general iterative optimization algorithm. And now I'm just going to think about some arbitrary function f of x from Rd to R, and I'm going to assume that we're trying to minimize f of x, or for x in Rd, right, just to fix this. All right, so the general optimization algorithm is as follows. You pick a point in Rd. Pick it any way you like. So pick x0 in Rd. All right? And now you're going to iterate. So I'm going to write it as kind of in pseudocode as a for I equals 1, 2, 3. That doesn't mean you would actually write it as a for loop. You might write it as a while loop or whatever, but I'm just going to write it like that. So here's what I do. Given where I am now, I need to make two choices. One is I need to make a choice which direction I'm going to walk in. Sorry, this should be Rn. My dimension is always n, so Rn. Okay, so I need to make two choices. I need to choose a direction, and once I choose a direction, what's the other thing you need to choose if you're gonna go uphill or walk? Sorry? Well, your speed or like how far you're gonna go in that direction. Okay? So the first part is choose a direction. I'm gonna choose a vector d. Sorry, I stumbled a bit. I let this be d, but n will always be the dimension of our domain. D, in this case, is a vector. So I'm going to let it be a vector in Rn, right? So what is a direction in three-dimensional space? it's a vector, that way or that way or that way. But I don't care about the magnitude of the vector, right? If I point you that way, I don't care if I'm pointing you that way with like this arm, or like I have a smaller arm or an intermediate arm. So what I'm just going to insist on is that for us, a direction will be a vector of length 1, right? All I care about is which direction it's pointing. I don't care about the magnitude. So this is your direction. And then I'm going to choose a step size. And that's just going to be a number. How far do you walk in that direction? Okay? And then the idea is, for wherever you are, you're going to move in the direction d for a length s. So in terms of an iteration, I'm going to call this di. This is my ith choice. And I'm going to call this si. And what you'll get is that xi will be xi minus 1 plus si times di. So let me just so that the notation doesn't bog you down. Right, so if imagine I is equal to 1, then I pick a direction d1, I pick a step size s1, and what I'm saying is x1 is going to be equal to x0, which you just picked, plus the step in the d direction. Okay? And then I repeat it. So let me show you, if I draw you a picture, it might make more sense. So imagine the only picture I can draw is when n is equal to 2. So I'll imagine that n is equal to 2, okay? So if n is equal to 2, then your domain is the Cartesian axis. So this will be x1 and x2. This is your domain. I pick an initial point. Let's say this is x0, right? So that's my initial point. I pick a direction. So maybe I pick the direction d in this way. Call that d1. Once I pick a direction, then you can walk any amount along that dashed line. Right? You can walk any amount you want. The step size tells you how far you walk. So you pick some step size, S1. Oops, sorry. Oops. So you pick some step size S1, and that puts you at the point X1. And X1 is simply X0 plus S1 times D1. All right? So now you're standing at X1. You pick a new direction, call that D2. That D2 defines for you a line. And even in three-dimensional space, it'll define a line, right? A direction, you'll move along a line. You take a certain step size, call that S2. And that puts you at the next point, which is X3. So, sorry, am I at X2, I should say. X2. So the X2 is X1 plus S2 D2. And so on, right? No, you choose a different S every time. And you choose a different D every time, right? So you change your direction, you change your S. The only thing we're going to agree on, just because, is that S will always be greater than or equal to 0. So that, like, I don't walk backwards. And the reason I don't want to do that is because then the direction isn't the direction you're walking. It's actually the negative direction. So we'll just always assume that the step size is positive. And if you want to walk backwards, flip the sign of your direction. Any questions on that idea? So that's it. But yeah. Yeah, so in so far I haven't told you anything about F, right? I mean, when do I stop? How do I choose D? How do I choose S? Those are specific to the method, right? So what'll happen is that different algorithms, so this is always going to be the case. I'm not aware of any optimization algorithm that does anything different than this, more or less, right? There, you know, you can do a little bit of things, but basically this is it. You pick a point, you pick another point, you pick another point, you pick another point. Different algorithms choose D and S in different ways. All right. So today, to start with, I'm going to show you one specific algorithm called steepest ascent, or steepest descent here, because we're minimizing, that'll choose it in a specific way. Any questions on that? Right. So as I've given you here, this is completely useless because you don't know how to pick D and you don't know how to pick S. What it does for us is it provides a general context. This is the iteration we're going to see over and over. Okay. So any ideas? What would be a good choice for D? If you have the function f, so I give you f, and you can take any derivatives you want. How would you choose the direction? Any ideas? Which derivative, right? I'm in multidimensional space. Yeah. You go, why the gradient? Yeah, so our first choice is going to be to choose D as the gradient. But I'm going to throw out a question now, and I'm going to, what about this algorithm? What about the following algorithm? For choosing D. So suppose this is my x0. All right, so I'm just redrawing what I wrote before. This is x1 and this is x2, and this is my x0. Why not check a bunch of points around you, right? That's what we would do visually, right? If you're in the example I gave you, if you're in some forest, you would turn your head around and you would look, and you would pick the place where you're going up the fastest, right? So the equivalent here might be, I'm just going to check a bunch of points here. What's wrong with that? And then I'm going to pick the point where my function grows up. If I'm maximizing, then I'm going to pick the point where my function goes up. So I might let's call this point Z. I'm going to check f of Z versus f of x, 0. And depending on whether I'm maximizing or minimizing, Z will either be better or less than x0. What's wrong with that? Yeah, but it doesn't look too bad. Sorry? Yeah, but I can calculate all of these. Look, I've written, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points. It shouldn't take me that long to compute. But based on what you've done so far on homework 1, why will this be very, very difficult to implement? There's 2 things I can think of. Yeah. This is, if you're in 100 dimensions, this is not going to work. Because what is a simple circle here will be a 100-dimensional sphere, and you're going to have to pick a lot of points. In fact, the number of points you pick is going to grow exponentially with the dimension. Right? You can think of it here, maybe I can pick 4 points, north, south, east, west. But in 100-dimensional space, there's 100 directions. You'll have to pick 2 to the 100 points. Right? And you'd have to, or at least 100 points, but then if you do combinations of it. So the dimensionality, this will collapse just like what we talked about before. In high dimensions, you can't just look around you. And then, but even in 2 dimensions, what would be the objection now? think a bunch of you ran into this when I asked you to do exhaustive search. What was hard about exhaustive search? One other thing. Yeah, like the width and the grid size. So here you'll have the same thing. So how do I know that this circle isn't like 100 miles from this point, right? What's the scale here? How far away should I test my point? And how many points exactly do I need in this circle, right? So you'll get into this issue that you won't know kind of how big to make this circle and how many points there are, and you'll have to do all this tweaking. That's not to say that these algorithms of this form do not exist. They do, but they're difficult. They're difficult for the same reasons that exhaustive search is. Okay. So one choice, as was mentioned, is choose. So this is called steepest ascent if you're trying to maximize f of x, and otherwise it's called descent if you're trying to minimize f of x. So I'm going to stick with maximization for now. So let's think about maximizing f of x. So what I'm going to do is my direction is going to be grad f of xi. So wherever I am, or actually that should be xi minus 1, sorry, xi minus 1. So wherever I am, I'm going to take the gradient, and I'm going to move in the direction of the gradient. So how many are familiar with the fact the gradient points in what direction in terms of the function? If I walk in the direction of the gradient, what can I be assured of in terms of the function? Sorry?
Function can increase.
Increase. But what else relative to other directions? At the greatest rate. Can you guys prove it? Who can prove it? Okay, we're not going to worry about proving it right now. We'll prove it later. But I just want let me just make sure everybody's on board with that. Who's familiar that the gradient points in the direction of steepest descent? 1, 2. Okay, so let me show you. Let's see. Okay, this is a good picture. So here's your domain. This is your x and your y, just like our x1, x2. Here it's y. And up here is your function. So this is the value of your function. You're at this point. This is x0, and you compute the gradient, and it points in this direction, right? So this is my d. Up here, the result is that if you walk along the gradient, then your function increases at the most rapid rate. Right? So if I move this way or this way, or I should write right here. If I move in this direction or this direction, I will increase, but slowly, relatively slowly. The direction of the gradient is the direction where the function increases the most rapidly. We'll show that in subsequent classes. Let me see if there's another picture that's nice. Let's see. Oh, this one's a little more. This is the same idea. Here's my point, right? And the gradient, here they're showing you the gradient up here, but the gradient, I don't know if you guys can see this light green here. That's the gradient. It says grad f. And if you walk in that direction, your function, the value of which is graphed here, increases the fastest. But what's important is it's not the case that the function increases forever in that direction, right? These are functions that can take on any shape. So if you walk too far in the direction of the gradient, like if I walk 700 miles in that direction, yeah, at first I'll go up, but then I'll go down, and I may end up going kind of in this lower hump here. Okay? So for now, all you need to have in your head is that if I move in the direction of the gradient, I'm guaranteed of moving in the steepest direction upward. Okay? No, it is the only direction. Unless the function is constant, it is the direction of steepest descent. Yeah. And unless your function is not differentiable, right? Once it's differentiable, the idea is that it's really a reflection of the tangent plane. And once if you think about a plane that's not horizontal, if you think about a plane and you ask which direction do I walk on to kind of go up the plane the fastest, there's only one. And that's why. Any other questions? Okay. So hopefully, if I've not convinced you, I've at least reminded you or set the scene for why we choose this. Right? So then we just have to choose the step size, and as was mentioned, we also have to choose when we stop. So there's all kinds of flavors of steepest descent. So let me do steepest descent version 1. So I'm going to pick some x0, pick it in any way you want. Usually you know something about your function, so you should have some good initial guess. And then my general optimization becomes the following. I let d sub I equal grad f of xi minus 1. And then it's usually good to normalize it, right? To divide it by its length, because that way the direction is of length 1. Okay, that dividing by the norm just makes di of length 1. Step size. What should I do for the step size? Any suggestions? What's the simplest thing I can do? All right, just fix it. Just pick something. Let me just for the sake of, I'm not picking exactly one. Let's say I pick 0.2. That's my choice, right? And then I update xi is equal to xi minus 1, where I was before, plus a step of length si in the direction di. And that's it. When should I stop? So this will iterate, right? At each, I'm not going to draw the picture again, but you pick x0, you pick a direction. In this case, the direction has been, there it is. And off you go. When should I stop? Any ideas of a stopping criteria? Right, so stop when the norm of the gradient, asking it to be exactly 0 is too much because there's going to be round-off errors in the computer. And also, your step size is fixed, so you kind of don't have your granularity. So usually you ask that it be small enough, less than some epsilon. So this for loop typically is a while loop where you check the gradient, and if it's less than some epsilon, then you stop. And you usually have iteration, or like you cap it at like 20,000 iterations or whatever, and you go through it. Any questions? So what's the criticism for a fixed stress? Yeah, right. What if everything is in units of miles and my optimum, my maximum is 50,000 miles from x0, and I'm walking steps at 0.2. You're never going to get there. What else? There could be also a reverse. Yeah.
Yeah, I was going to say, is it possible that it's a larger distance?
Yeah, right. What if my mean maximum is very, very close to me? Or more, maybe a better objection is this 0.2 might be a lot. Right? What's the scale of the function? 0.2 might be a ton, and kind of it's like as if I'm telling you, okay, you can only take step sizes of 20 miles. Walk to Baltimore. Well, you're gonna right? You're gonna maybe Baltimore's a better example. What would be a good example? Arlington. Yeah, go to Arlington, but you can only take 20-mile steps. It's hard, right? I mean, you kind of loop around, and so that, I mean, it sounds funny, but that's exactly the type of thing that can happen, right? That you take these big steps and you end up jumping around because you can't get close to the minimum. So this is an issue very similar to what you saw in exhaustive search. Kind of in the optimization community, this would be frowned upon. But this is how most machine learning occurs. In machine learning context, this SI is called the learning rate. This is called the learning rate. Learning rate. And then if you read like, it's not so much anymore, but if you read like from 10 years ago or 20 years ago, these kind of machine learning optimizations, they'll start saying things like, well, if you set the learning rate too low, then it'll take you too long to learn, meaning too long to find your minimum or your maximum. If you set it too high, then you're being too ambitious and you're trying to learn too fast. I mean, you're trying to get to Arlington in 20 months. Okay, any questions? So this is a fixed, so this would be called a fixed step size steepest descent. It's our first example of an iterative optimization. Okay. Any questions? All right, so let me show you how to fix, a simple way to fix the fixed step size, or to correct the fixed step size. So one thing you can do, right, if you take, you choose, the idea is, so let me call this steepest descent version 2. So this is fixed step size. And this is steepest descent version 2. So I'm going to do the same thing as before. I'm going to pick X0. Everything's going to be the same. I'm just going to pick the step size slightly different. And I'll let DI be my gradient. And I'm going to let, let's say I'm going to start by letting SI be, I'm just going to write a number down, 5, let's say, okay? So here's the idea of this is going to be what's called backtrack. So I give you a step size 5, right? So I take a big step size, and what I do is, what I'm afraid of is that I've gone too far. How do I know if I've taken too big of a step size? If I give you SI equals 5, and I ask you, is this a good step size? What would you do? But what would be, so what would the result? So okay, so you double it and half it, and then what would you do? So that's like you, so what if, all right, so what happens if they're all, so let's say we're trying to maximize f of x. And let's say you try 5 and then you try 2.5 and 10, right? And what would you check at 2. So you take a step size of 2.5, step size of 5, and step size of 10, and for each one, what would you do? So the gradient is here. What? If I give you 2 points, 2 x points, right? X and x tilde. And I ask you, tell me which one is better if I want to maximize f of x. What would you do? Right, you plug it into f and c, right? So going off of what you said, if you take a step size of 2.5, 5, and 10, you can take the x value that results from each one of those steps and plug them into f, right? And what would I do then? So I give you the 3 f outputs, and then what would you do? pick the biggest one. But what if they're all, what if we're in a situation where this is way, way too far? What would happen then? I mean, how do you know? So what you're doing implicitly there is you're comparing 5 to 2.5 to 10. But I want an absolute measure. Is this a good step size or bad, right? You're judging for me whether 5 is better than 2.5 or 5 is better than 10. But what's the mark of a good step size? Sorry?
I mean, if the step is too big, then short. Whether it's S is too small, maybe it's very tiny.
But how do I know whether S is too big or too small, right? I mean, what is it? I need to know, not like, I give you an S. S is 5. How do you know? How do you check, right? So here's what I'm going to do, right? I'm going to form this next xi. I'm going to form xi is equal to xi minus 1 plus si di. Now you have this xi. How do you know if that step size is good or bad? In kind of a very general way. Yeah, right? If you're doing work, and you're doing work in all these computations, you want your work to be productive, right? Unproductive work is very, very bad. What is productive work in this case? What would we want? So we require or want maybe that f of xi should be less than f of xi minus 1. Right? Surely if you're going to do all these computations, and I'm at a certain point xi minus 1, and then you give me a new point xi, and it's worse. It has a lower f value, and I wanted you to maximize f of x. You've just wasted my time, right? You've taken me downhill, and I want to go uphill. So you can come up with all these algorithms, and I should say that people do. Like yours is the beginning of all these different algorithms for finding things, for finding step size. But at its most simple, the simplest algorithm is just to ask, give me a step size that if I take that step size, I reduce the value of my function. Right? So here's the general idea. It's called backtracking. You aim big, right? You take what you think is a big step size, so not too big, but big, 5, let's say, and you check. If you went downhill, great. That's your step. If not, back up. See if you go downhill. If not, back up. Or I should say uphill, sorry, because we're trying to maximize. So let me say it again. You take the step size 5. If you went uphill, great, take it. If not, then go backwards. If you went uphill, take that one. If you're still going down, take back up and keep backing up. Yeah.
Wouldn't you require them not at the back side?
Yeah, this is reverse. I wrote it wrong. You're right. So maybe that's why everyone was looking at me weird. Yeah. You're absolutely right. What I wrote was the bad situation. Thank you. Okay, so let me then, before we do this step, what we're going to do is just simply a while loop, right? So what I'm going to do is while f of xi minus 1 is greater than f of xi minus 1 plus si times di. Right, so this is the bad situation. This is the situation where you are now, your function is greater than where you're going. And you want to go uphill because you want to maximize. So if this is the situation, you back it up, meaning you take a smaller step size. So you do si is equal to si divided by 2. And you keep backing up until where you step has a greater f value than where you are. So this while condition is false. And then you go down. So now after you do this while loop, you do the update. xi is equal to xi minus 1 plus si di. And then you have to have a stopping condition where you check for the gradient being small enough. But And this is referred to as backtracking. Okay, any questions? Does that make sense? You're gonna have to code it. Yeah.
So the end up being go backwards and go that back into John, you're saying to next to the step, so in this case, to get step 5. Yeah.
Sorry.
Let's say you that back situation.
Mm-hmm.
Once you get that while, you're saying next to the step 5.
Yeah. So how does that strike you?
Because we can overshoot again.
Yeah. So there's different algorithms. So let's walk it through, right? So first of all, should I be like, let's say, should I be super aggressive here? Should I choose very big number, medium number, small? What are the pros and cons? What if I choose a very, very big number? Right? Like I want to get to Arlington and I choose 20 miles. What's my price going to be? Yeah, your while loop is going to run for a long time, and why is the while loop expensive? Dividing a number by 2 ain't so bad. Yeah, the logical check is very fast. It's right, but involved in that is this computation. Every time you do the while loop, you've got to compute the function at the new points, right? So this is going to cost you. So if you want to be, you say, oh, well, great, I can always backtrack. I'm going to choose S huge. Well, then you're going to pay a price for backtracking too much. If you choose S too small, then you won't backtrack at all, but then you won't make good progress. So you always want to choose S in the middle. Now then the question arises of what you raised. Should I reset S in every iteration? That is, in the previous iteration, I found, let's say, that my step size ended up being 0.1. Should I, in the next iteration, try and take a step of 5 again? Or should I do 0.1? Or should I do something else? What do you guys think? 0.1? What if I back it up then to 0.01? What do I do then? Do I do 0.01? Well, then I'm taking tiny, tiny, tiny steps, right? So if you take out this line, what will happen to you, I'm just telling you it will, is that this S will get smaller and smaller. You'll back it up to like say 0.1, and then when you come into the iteration again, S will be already 0.1, and you'll hit some area of the function where you kind of got to wiggle around, and then S will be 0.01, and then maybe 0.0001, and then you'll hit some place in the function where you really got to cruise, right? It's really uphill, and you got to take these big steps. You won't be able to. You'll be taking this tiny little 0.01. So I'll leave it. It's a great question. I'll leave it to you to think through algorithms, and you can do this. But there's a middle ground between setting SI equal to 5 and always resetting it, and not resetting it at all. You can allow yourself a situation where you always try and go a little bit bigger than you were, so you can kind of stretch yourself out or stretch yourself down. But I'll leave it to you. So you put your finger in practice. The algorithms are a little more involved than this. Any questions? Okay, so I will tell you that every time I assign this for a homework, many people, not many, like some significant percentage, forget this, and then they don't converge, and then I get an email. I've been running it for 8 hours. Is it supposed to take that long? And I don't know. I don't know what processor you have. I don't know what you wrote, but so be careful. So just bugs. Be careful of this greater than or less than. Think it through, like which way you have to go, and be careful with that. Okay. Any questions? Yeah.
So we said X1, but then that we need to use it again.
X0, you mean?
XI.
So xi, and then on the next iteration, xi will become the xi minus 1, and then you use it to compute your new gradient. Does that make sense?
Yeah.
Yeah. So this is steepest ascent with backtracking. With backtracking. So let me just make, where are we for time? 7:20. Okay. So let me just make one more comment. What if we're maximizing? What if we're minimizing f of x? What should you do then? So you don't want to go uphill anymore. What's the modification? Yeah, send it to, so then it's steepest descent, and I don't know if oh, no, I didn't. So the idea is that the gradient is the direction, again, this light green arrow, the gradient is the direction of steepest ascent, but if you walk in the negative gradient direction, so exactly the opposite, that'll be the direction of steepest descent. So that's so if you're maximizing, you walk in the positive gradient direction. If you're minimizing, you walk in the negative. That's okay. So then everything is the same, but you choose your direction equal to negative gradient of f of xi.
Did you also change the control of the logic?
Yes, that's another thing that there's usually bugs on, because if you don't change that, you're not exiting the while loop sometimes. So I should do and change while loop condition, and this is called steepest descent. So most machine learning algorithms use steepest descent. Any questions? Yeah. Yeah. Because so that's a great question, right? What happens if I do this? What happens if well, let me clean it up a little bit. So let me write it. Let me just rewrite it so it's all clean. So what happens if I do this? So let's imagine, just so I won't have to write it. Let's imagine I'm doing my fixed step size. What happens if I don't normalize the gradient?
You don't want to change.
Yeah. So what do you mean by that?
So if you normalize it, so it's one,
So what concept? Right. So this gradient, if I don't normalize it, will have different lengths, different magnitudes. What consequence will that have for me? Yeah. So this step size, setting it to 0.2, has not much meaning if you don't normalize the gradient, because you're not going to be taking steps of length 0.2. You're going to be taking the steps of length 0.2 times the size of the gradient. And what will happen, which is actually okay, is that if the gradient is really, really big, you will take enormous step size. And maybe that's good. So it's not the case that everything will fall apart. It might be okay, especially if you use backtracking, you'll be okay for sure. If you don't use backtracking, then this can be a little bit, it's just a wilder algorithm, because you, especially if you know something about the scale of your function, like you know that the x values kind of change, that the function changes on a scale of like 10 or something, then you can encode it into that step size. Si is equal to 10. But if you don't normalize the gradient, that won't have any meaning. Does that make sense? Okay. Having said that, people do this all the time.
because it costs, especially if you're in very high dimensional space. So if your gradient is of length, like if you're in like 1 million dimensions, then just normalizing it costs something. So people won't do it. So, so it can work without it, but then the step size is not really the steps.
Okay. Any other questions? Yeah.
So this code only applies to situation where you have one maximum. If we have like 2 maximum, and these 2 are very close to each other, maybe this will go into loop dynamic.
Yeah, so that's a great question. Let me just, I realized we were minimizing and I wrote so the gradient should be negative there. But yeah, so in general, so I should write our goal is to find local mins and local maxes. The question, so these algorithms will not find you global mins and maxes. And we'll talk about that more. In general, if you give me a function without just, without saying anything else, and you want me to find the global min, I can't do it. I can't do it. And that's just generally true. So you'll in general optimization, we can't find the global without any other characteristics of the function. And you can think it through that, like if I'm here and I have the function around me and I find some local min that looks really, really good to me, how can I rule out that, 50 million miles from here, there isn't some global min lower? There's just no way for me to know, right? So in general, minimizing a function is not achievable in a computationally reasonable amount of time. Basically, it requires exhaustive search. But what we will talk about is that there are certain classes of functions, the convex functions, where if you minimize if you find a local min, it's the global min. So the short answer to your question is we can only guarantee local and mins or maxes, but we will talk about it a lot more. Yeah. Okay, any other questions? Okay, let me just check the time. 7:30. Okay, 15 minutes. It's awkward. Okay, well let's start root finding, and then we'll only do 15 minutes, and then we'll continue it in after the break. So let's see. Okay, so we've done 1, we've done 2. Now we're going to talk about this. So I'm going to tell you where we're going, but I'm not going to connect it there right away, and I might wait till next class to do it. What root finding is going to do for us, root finding is just of interest in its own right. So for example, you're encoding a square root function. I don't know why you'd want to do that by yourself, right? I mean, you might say, well, there are square root functions in R, but root finding just arises in different situations in its own right. But for us, what root finding is going to do especially is it's going to do this, right? That we're going to want to set the gradient equals 0. So it'll be a different way of finding the mins, of finding minimizing or maximizing. So just to show you where we're going. But put that aside for now. And let's just remember, so back to root finding. And I want to tell you about one-dimensional root finding, which we did last week, and multi-dimensional. And I'll tell you the difference. Okay, so one-dimensional root finding, 1D root finding. You have a function, let's call it h of x, which goes from r to r, right? So it's like a Calc 1 function, and you want to find its root, right? So here's x, here's h of x, and you want to find its root. So you want to find this point right here, okay? And just be sure, forget about optimization now, because we're not optimizing this function. We're finding the root, which is different, right? We're finding where it crosses the x-axis. Multi-dimensional root finding is that you have a function h of x, which is a vector of functions. Let me do h1 of x, h2 of x, all the way to hn of x. And each hi of x, meaning each one of these h1, h2, all the way to hn, each hi of x is a function from Rn to R. Okay? And we would like to find an x. So, sorry, here I should have written we want to solve hx equals 0 on the left. On the right, we want to find hx equals 0 again, but just remember that in this case 0 is like that. Okay? So actually, you've been doing this for a long time, whether you know it or not. So a simple version of this, of multi-D root finding is something like this. 3x, let's say 1 plus x2 plus 5 equals 0, and 5x1 plus 3x2 plus 2 equals 0. You've done this before, right? You have simultaneous equations. That's multidimensional root finding. Because what I can do is, I'm going to just reminding you up top here of the notation, what I can do is collect two functions that represent those two equations. So I'm going to let what's on the left of that equal be h1 of x. So h1 of x is 3x1 plus x2 plus 5. And let h2 of x be this other one, 5x1 plus 3x2 plus 2. And then this becomes equivalent. I think I mentioned this, but when I write three like a triple equal, I just mean it's equivalent problem of defining a vector function h1 of x, h2 of x, and I want it to be 0, 0. Okay? So you've done multidimensional root finding before. You just didn't call it that. Any questions? So this multidimensional root finding is easy because it's linear and it essentially involves matrix conversion. A more complicated one is when the functions become nonlinear. So as an example, nonlinear root finding so if I do h1 of x is equal to, I don't know, I'm just going to make something up. Sorry. Right, so your h1 now is this complicated nonlinear function, and your h2 of x is, I don't know, so don't take what I wrote down too seriously. I just want you to see examples of two nonlinear. So this maybe you haven't done before. Has anybody done solutions, right? Because so the difference, and you've seen this hopefully in your homework, is that what they taught you, whoever it was that taught you, was that the way you solve this is you isolate one variable in terms of the other and then substitute, right? That's how you do it.
But that falls apart when you cannot isolate a variable, which you cannot do here or here. I think, if I get it right. So you can't do what you did up here. Right? So, and then you can imagine, you can imagine more equations with more variables. One important piece of this is, what if I didn't give, I have two coordinates and two equations. Why is that always the case? Why can't I give you an example of, let's say, for instance, 2 coordinates and 3 equations? Why can't I put another one here?
Why should you be suspicious if I demand something like this? Yeah, right. So put and use this one up here as a touchstone, right? So if I gave you another equation here, 8x1 plus x2 plus 3 equals 0, what would be your objection here?
If I give you 3 equations and 2 unknowns, your unknowns are x1 and x2. And I've given you 3 equations. What would you tell me? Different. Well, what if I want all of them? Well, what would you tell me? Yeah, there's no solution, usually, right? So in general, I cannot satisfy 3 equations with 2 unknowns. And if I only gave you 1, what would you tell me then? If I only gave you that H1, what would you tell me then? Yeah, there's infinitely many solutions, right? So in general, if I want to kind of give you a reasonable problem, I should give you the same number of unknowns as equations, right?
So so I wouldn't give you a third, and I wouldn't give you a third here. And that's why up here, just to make that point, and maybe that'll be a good time to stop.
So here, I kind of did it without saying, but my domain for each one of these HIs is n dimensional. That means you have n variables, like x1, x2 to xn, right? This is the number of variables. And then how many equations you have is the number of h's, which is also n. So generally, in multidimensional root finding, the domain should be the same number as the length of the vector that you're sending.
This is a good place to stop. So it's a little early. It's 7:40. So let's come back a little early at 7:55. Okay.